In this video, we're going to review the idea of the Heisenberg Uncertainty Principle and what kind of information we can glean from that. So I think everyone kind of knows the Heisenberg Uncertainty Principle has something to do with you can't know the position and the momentum at the same time. And there's this expression I've written here on the screen that says the uncertainty in position times the uncertainty in momentum is always greater than or equal to h bar over 2, which is some very small constant. And that's true, and that's a general reflection of what the Heisenberg Uncertainty Principle is. But there are, in general, there are other functions as besides position and momentum that we can't know simultaneously. So these also kind of get wrapped up in the uncertainty principle. So there's a number of quantum mechanical operators that we can't know they're observable simultaneously. And this goes from, in the last video, we talked about commuting operators. So for any two quantum mechanical operators, if they don't commute, we can't know them simultaneously. But what we have here for the Heisenberg Uncertainty Principle is specifically a relationship with position and momentum. So we're going to carry on with that. And you can see here the fact that we are multiplying the uncertainty in position with the uncertainty in momentum implies that not only can we not know them simultaneously, but there is a trade-off. So if our uncertainty in momentum is high, maybe our certainty in position is also high. So the more we know about position, the less we know about momentum, and vice versa. So we can go ahead and explore that by thinking about the free particle. So recall the free particle has a wave function of the form the wave function is equal to e to the I k x. So this represents, again, some sort of sine and cosine terms, a traveling wave. So the question we can ask is this an eigenfunction of the momentum operator? And that's important because if it is an eigenfunction, we exactly know its momentum. So the momentum operator is minus I h bar, and it's one derivative with respect to x. And if you're good at your derivatives, you can already see that this is in fact going to be an eigenfunction of the momentum operator. So we can operate on our wave function with the momentum operator. That's going to give us minus I h bar times I k e to the I k x, which is going to equal h bar k e to the I k x. And this shows us that our wave function is an eigenfunction of the momentum operator, and that means the momentum is exactly this value hk, so h bar k. So we exactly know the momentum of this particle, this free particle. We can describe as momentum. So if we exactly know the momentum, according to the Heisenberg Uncertainty Principle, we would expect that we know nothing about the position, and that's what we see. So remember, to calculate the position of a quantum mechanical particle, we can never quite know, but we can know its probability. So the probability of a quantum mechanical particle is equal to the complex conjugate of the wave function multiplied by the wave function. And then we can integrate over that in specific regions and figure out what the probability of finding it is. What we're going to need to do here for the free particle is, remember we did this in class, the book goes over it, but we have to divide this by 2L, and this is normalizing it, so we're going to give a probability of 1 in our arbitrary length L. So this 2L on the bottom is just for normalization. So what is the probability here? Well, we take the complex conjugate of our wave function, which is e to the minus ikx, and then we multiply that by e to the ikx, divide that by 2L, and we end up with just simply dx over 2L. So what does this mean? If we were to evaluate any integral here, we just basically have 1 over 2L times the integral of dx. So what we're going to find is if we integrated over the first half of the box, we would end up with a dx of 0.5, which is telling us we have a 0.5% chance of finding it in the first half of our arbitrarily large box. And so what this means is that our position, our probability of finding our particle with respect to position, is independent of position. And so that means that our particle is essentially anywhere in the box. We have no idea where the particle is. It has an equal chance of being anywhere in the box. So that is what we would expect. So we exactly know the momentum, and we know absolutely nothing about the position. But what about this trade-off? So can we lose information about the momentum? And does that gain us information about the position? And we'll find out that it does. So how do we lose information about momentum? So we can imagine that our wave function, instead of just being this e to the ikx where we exactly know the momentum, is rather a superposition. So maybe it's e to the ik minus 1x plus e to the ik 0x plus e to the I k1x. So now if we ask what the momentum was, well, we don't know. We know that our wave function is a superposition of these three operators, or of these three eigenfunctions. So that means our momentum could be h bar k minus 1. It could be h bar k0, or it could be h bar k1. It's one of these options. We don't know which option it is. So by doing this, by making our wave function a superposition, we have lost information about the momentum. Instead of exactly knowing the momentum, we know that the momentum has a certain chance of being any one of these three options. So what happens to the position when we do this? We could look at this in two ways. We could actually go and evaluate this expression up here for our new wave function. That would be cumbersome. So what we're going to do is just plot this on a graph and see what happens. So I'm going to switch screens here, and this is an image of this wave function. So here we have our wave function just simply being one eigenfunction. So we exactly know the momentum. You can see we have no idea where the particle is in this window. But if we increase this a term down here in the bottom, that's going to be adding more and more terms. So as a gets bigger, we're less and less certain about the momentum, and then we're going to see what happens to the position. And so the plot here is showing the position. So we can see that we know nothing about the position at a equals 0. But as we increase a, so here we're at a equals 6, we can see the particle begin to localize. So now we have a greater chance of finding the particle in the middle of this region and a lesser chance of finding it at the end. So we are less certain about what the momentum is, but we are now more certain of where the particle is. It's more likely to be found in the middle. And as a gets larger and larger, we can see that that certainty becomes even more pronounced. So let's go all the way up here to a equals 100. We have a very, very, very large chance of finding our particle in the center and a low chance of finding it anywhere else. And we now at a equals 100, the way that this is set up, is we have 201 different possible momentums. So we know almost nothing about the momentum, and now we know almost everything about the position. So we can see we get this trade-off here, and you can imagine a world where we completely change this and know everything about the position and nothing about the momentum. So that's essentially what's going on here with the Heisenberg Uncertainty Principle. We have two quantum mechanical operators. We can't know both of them simultaneously, but there exists a trade-off between them. So learning more about one of the operators loses us information about the other, and vice versa.